So thanks for the introduction. I'm very excited to be here. I'm going to talk about Oblivious RAM today and how it evolved from theory to large-scale real-world deployment. And I'll also talk about why ORAM is important for blockchain applications. Okay, so I'll start with the success story for Signal, and now I'll talk about what is Oblivious RAM and how these algorithms work. And at the very end, I'll mention other applications in blockchains and what are the real-world challenges we encounter when we try to deploy ORAM. Okay, so as I said, I'm going to start with the non-blockchain application. So Signal, they have a user database, and when you I don't know, some of you may actually use this application, right? It's a private messenger. So when you sign up to use Signal, you might want to discover which of your friends are also using Signal, so you can get connected with them. So Signal offers a contact discovery service. And this is what they want to do. So let's say David goes on Signal, and Signal says, okay, why don't you send me your address book, and I can tell you which of your friends are on Signal. But I mean, obviously, David is concerned that he doesn't want to leak his address book. So how do we solve this problem? Here's a naive idea. So it turns out Signal uses trusted hardware in the cloud. They have Intel SGX running on their servers. So one thing you can immediately think about is, so what is trusted hardware? Trusted hardware creates a secure hardware enclave or secure hardware sandbox. And everything outside this sandbox is encrypted. And there is a decryption key inside the sandbox that can decrypt the data. And you can do computation inside the sandbox, right? Okay. So one thing you can do is have all the data encrypted, like in transmission and also in storage, and only decrypted inside the enclave. So in this case, basically, you don't reveal the contents of the data. It may seem like this would solve the problem, but it turns out it's actually well understood. Encryption alone is not sufficient for ensuring privacy. And in this particular case, access patterns to even encrypted data can leak very sensitive information. And here's why. So in this application specifically, you have this large database sitting in memory and on disk. And if the operating system can observe like which locations you are accessing, and this is sufficient to leak which are your friends, because you are accessing your friends' records. Okay, so I also want to quickly mention that simple solutions like randomly permuting the data in storage doesn't actually solve the problem, because like you can still pretty much learn the entire social network graph. Okay. So this access pattern leakage problem is actually a very general problem. It exists in many different scenarios. So for instance, we can think about it from a programming language perspective, right? So here is, you don't have to look at the code. This is just binary search. So if you think about how binary search works, you look at the middle, and depending on the result of the comparison, you either look on the left half or the right half. And if you observe all the access patterns, you can immediately learn which value you are searching for. You reveal the query entirely. And more generally, if your program has an if branch that conditions on some secret variable, let's say, if the last bit of my secret key is 0, I access memory location X, otherwise I will access memory location Y, then by observing which memory location is accessed, you leak the value of the secret variable. And so also this was an attack that was performed by some researchers from Microsoft Research and UT Austin. And they show, so if you are running this off-the-shelf image processing software inside SGX enclave, and you can only observe very coarse-grained page-level access patterns. And even such coarse-grained access patterns are sufficient to basically reveal the shape and the location of these objects. So it is very leaky. So therefore, the problem we are interested in is how can we probably obfuscate access patterns, but we want to do so in a way that preserves efficiency. So this is the big question we want to solve. And let me tell you the Signal's trajectory. So back in 2017, they were launching this private content discovery service. And the first idea they come up with is kind of like a naive idea. So imagine I want to search for my contacts. They would linearly scan through the whole database and find the matching entries. I mean, of course, in this case, you cannot learn which locations are matched. I mean, of course, this is very expensive because they have a billion-size database. So they made some optimizations, and they say, okay, we are going to do it in a batch. Once we gather a batch of queries, we make one scan through the whole database, but it's still going to be rather expensive. So the overhead is linear n divided by beta, where beta is the batch size. So back then, in order to handle the load, they had 500 servers. And then when it was 2022, they realized, okay, perhaps we should go for a better solution. So they deployed this scheme called Path ORAM, and this was the scheme I had back in 2013, joined with Emil Stefanov and others. I guess Ling is also a co-author of the paper, and he's also in the audience. So like this scheme has log squared overhead. So even though asymptotically it is log squared, it's actually more like log n, because these two logs are not the same. Like one log has a large base. So for that log, in practice, it's like 2 or 3. So really, from a practical perspective, this is like a log n scheme. And after Signal deployed Path ORAM, they cut down to 6 servers, and this is like almost 100x reduction in server costs. So I hope I got your interest in ORAM. So now let me tell you how ORAM works, and also what is ORAM. Okay, so what is ORAM? It's an algorithmic technique that allows us to provably obfuscate access patterns. And the security it offers is as strong as encryption. Basically, nothing is leaked. Like you can think about, oh, somehow we can encrypt the access patterns, right? So this may seem like it's magical, but I'll quickly kind of tell you how these algorithms work in a little bit. So ORAM was first proposed by Goldrick and Ostrovsky back in the 1980s. So here's what ORAM does. It takes, so let's say I want to read some logical address or write some logical address. And ORAM will translate these logical requests into a sequence of physical requests. So one request may be turned into multiple physical requests. And the security it offers is that essentially, no matter what logical request you have, the sequence of physical requests are actually indistinguishable. So in some sense, the physical accesses are independent of these input requests. So if you were to deploy it in a trusted hardware setting, the ORAM would be actually running inside the enclave. So this is like the trust boundary. Okay, so back then we started working on ORAM, and we noticed that in the earlier schemes proposed by Goldrick Ostrovsky, even though asymptotically they achieve log cube cost, which seems nice, when you look at these schemes, you realize they are very complex and they have astronomical constants. They're not basically implementable as is. And on the other hand, Goldrick and Ostrovsky, they also show that if you want ORAM, you have to pay a logarithmic overhead. So this is like something you have to suffer from. But there's also a big gap between the upper bound and the lower bound. And then after Goldrick and Ostrovsky, there are some works that try to optimize the original scheme by Goldrick Ostrovsky, but all of these schemes are in the same framework, and they kind of inherit the same drawbacks. So you can cut down to log squared, but still they're not practical. So we wanted to make ORAM better, and we realized there are 2 big questions. Like one is, can ORAM ever become practical, right? And second, can we bridge the theoretical gap between this upper bound and the lower bound? So over the next 10 years, we've been working in this direction, and we were able to solve both problems. And the answer to both questions, yes. The theoretical scheme and the practical scheme, they're not the same scheme. I mean, it would have been nice if they were the same scheme. So today I'm going to focus more on the practical side. Okay. So let me quickly tell you how to construct an ORAM, and then I'll wrap up with some blockchain applications. So to understand ORAM, the first thing you need to understand is if you only permute the blocks in memory, right? So let's say I store every block at a random location. This is not sufficient for privacy. And the reason is because if, let's say, I access the same location twice, then you can observe that, you can observe the frequency of each location being accessed. You can also observe a high order statistical information like co-occurrence. And then this will allow you to do a statistical inference attack. And the reason why this naive approach is not secure is like pretty much the same as why deterministic encryption is not secure. Okay. So the key insight we should gain from this naive approach is that it seems like after I access some block, I have to relocate it. Because if I don't relocate it, next time I access it, I will go to the same location and it reveals statistical information. So you can keep this key insight in mind as I go over the scheme, because this key insight will show up. So we propose a tree-based framework for constructing ORAM. So essentially, there's a tree. Every bucket has constant number of slots. And in every bucket, we store both real blocks and dummy blocks. So the real blocks encode data, but the dummy blocks are just there for security. So actually, I'm calling them filler blocks rather than dummy blocks. So the filler blocks are just there for security. Okay, so here's the most important invariant of the scheme. I'm going to first cheat a little bit and assume the CPU can store a position map. Let's say this is stored inside the enclave. But this position map is going to be very large, but later on we can get rid of it. So this position map stores for each block X, which path it resides on. So the path invariant says every block will reside on some path. It means it will be in some slot on this path, and we don't know which slot it is in. So if I want to read block X, I simply have to look up the position map, find out which path it is on, and I read that path, and I'm guaranteed to be able to find the block X. So reading a block is very simple, as I said. You just go to the path X resides on. But the key point, as I said, is after you read the block, you have to relocate it. So you need to remove it from this path. So by the way, I want to mention, imagine all the data is encrypted. So the only thing the adversary can observe is the access patterns. Okay. So now I want to assign it to a new path. And the question is like, which path should I pick? So the most natural idea is I'm going to just pick a random new path and assign it to this random new path. So suppose I happen to pick the green path and I want to write it, like in order not to break the path invariant, I have to write it somewhere on the green path. And here's a slightly more tricky point is where can I write this block on the green path? I also just keep in mind, I also update my position map to make it consistent. Okay, so where I can write the block X on the green path? First, can we write it to the leaf node? Well, it turns out the answer is no, because if I just write it to the leaf, I reveal which path it is. So the next time, if I'm accessing the same block, you can observe, oh, okay, you know, I go to the green path. So this leaks information. You cannot reveal which path it is. And for the same reason, you should not write it to any of the internal nodes because these leak partial information about which path it is as well. So the only safe place for you to write the block back to is the root. The root is on every path. If you just write it back to the root, it doesn't leak anything about which path it is on, right? Okay. So I haven't, this is not the full scheme yet because you cannot keep writing things to the root. The root will soon overflow. But ignoring this overflow issue, you can see why the scheme has security is because whenever I choose a new path at random, as long as I don't reveal which path it is, the next time I access a block, it's just going to go to a random path. So every time I want to access something, it goes to a random path. So the security proof is actually trivial. Okay, so what is the remaining problem? As I said, the remaining problem is I cannot keep writing things to the root. It will soon overflow. So I will very quickly talk about how to resolve these two remaining issues. One is how do we prevent overflow? And second, how do we remove this position map I mentioned earlier? So for removing overflow, essentially we will have like an eviction process that you can imagine it's like some background maintenance process that tries to move the blocks closer to the leaf. And if you do this maintenance process cleverly, we can guarantee that there's no overflow with high probability. And the specific idea used in Path ORAM is you just like, if you are reading this path, you will do eviction on this path as well. And when you do eviction, you try to move these blocks as close to the leaf as possible without breaking the path invariant. So it's very simple, but the scheme is very simple, but the proof is non-trivial. Like proving that it doesn't overflow requires a complicated stochastic analysis. Okay, second problem, how do we remove the position map? The answer is one word, recursion. And what do I mean? You have a position map. This position map is a constant factor smaller than the original memory size. I'm going to recurse and put it in a smaller ORAM. And after log n steps, my position map becomes constant in size. I can just store it in my CPU register. So, so the scheme has log square cost, and one of the logs come from the recursion. And this log has a large base because actually, if in the same block, you can store the positions of multiple blocks, that is the fan out for that log. And in practice, this log is like 2 to 3. Okay. So this is like the pseudocode for the scheme. It's 16 lines, right? And I'm even counting and if and for. You can print it on a T-shirt. Essentially, it's a binary tree data structure, and I think it's actually much easier to implement, let's say, than a balanced binary search tree in terms of complexity. Okay, so just to quickly summarize, this is tree-based ORAM, and these are simple data structures. Okay, so to conclude, I want to quickly mention about the applications, especially in blockchain environment. And I want to quickly mention like some of the challenges for practical deployment. Okay, so when do you need an ORAM? So pretty much whenever you want to use trusted hardware, you need an ORAM, unless like your computation is very simple and uninteresting. Like especially when you need trusted hardware and then you are using it on top of a large database, like you pretty much need ORAM, like because simple linear scan schemes like what Signal did earlier, it is not going to scale. So this is another completely different direction, which I don't have time to talk about at all in today's talk. But actually, whenever you need multi-party computation, you also need ORAM, because like if you want to do multi-party computation, especially on big data, the same issue arrives because the same issue will arise, because like you can think of the multi-party computation as a crypto way to realize a trusted hardware. Okay. So why is ORAM important for blockchains? And there are actually many applications of ORAM in blockchain environments. We need it if you want to have privacy-preserving transactions and smart contracts, right? So there are various projects that they're building on Intel SGX, trusted hardware. So I won't go into details, but actually recently Andrew Miller did some analysis of these blockchains. And he and his students found that they don't give the promised security. I mean, there are many different reasons why they're not secure. And one important reason is because they're not using ORAM. Okay, and we also have companies like Flashbots. Like as we know, layer 1 is actually becoming more and more centralized because there are big players like Flashbots. And so it is important for Flashbots and other layer 1 companies to make sure they earn their customers' trust. So that's why they are thinking about using trusted hardware. And again, whenever you need trusted hardware, you need ORAM, unless you want to go for insecurity. Privacy-preserving lightweight clients, and this is actually being implemented by some blockchain projects like MobileCoin, and they are using ORAM. So I want to quickly mention, right now we are working on building an open source library called Oblivious STL. So you can imagine this is an Oblivious counterpart of like C++ STL. We will offer Oblivious counterparts for like common data structures, common algorithmic building blocks like sorting, shuffling, graph algorithms, and so on and so forth. And this open source toolchain is meant to like solve some of these practical challenges we encounter when deploying ORAM. So we have a few enemies. I guess one of the biggest enemies is lack of awareness, because think about Signal story, right? They didn't realize that there's this simple algorithm they can use back in 2017, and that's why they took this detour. And it's actually quite interesting to compare zero-knowledge proof and ORAM. because zero knowledge proof, like I guess there's more excitement in the community about zero knowledge proof. But zero knowledge proof, like the space is, I would say, it's there are many different schemes, but there's no one size fits all solution. So the space is very complicated. But in comparison, ORAM is a different landscape. Even though there's less awareness in the community about ORAM, actually ORAM, these Oblivious algorithms, they are very simple. They're simple algorithmic techniques. There's pretty much a unified solution for any computational task you want. And actually the barrier of entry for like developers should be much lower for ORAM than zero knowledge proof, because from from a theoretical or scientific perspective, this line of work is much more mature. Okay, I mean, there are also some other challenges, but I don't think I have time to go into the details. Like, for instance, one challenge is like, today what I talked about is a generic ORAM. If you have any computation task, you can just throw in Path ORAM and you will become oblivious. But if you have some concrete computational tasks, let's say graph algorithm, sorting, data structures, this may not be the best approach. There are other more efficient ways to turn your specific computational task, make it oblivious. So this is why we want to offer this STL library. And if you want to deploy ORAM for like Intel SGX, there's like a slight mismatch of the performance metric that this line of work used on paper versus the actual performance bottleneck. So the algorithm line of work focused on the computation overhead, whereas in practice, if you are in an SGX type environment, the number of page swaps is actually the dominant cost. So you actually want to optimize for a slightly different metric than what's written in those papers. And the security of implementation, it's actually not so easy to make sure your implementation is actually secure. Like, for instance, this is what we found in, this is Oblivious is like an Oblivious map implemented by a group in Berkeley. And we noticed in their code, like they actually don't offer the promised security because like here you have a conditional branch dependent on some secret variable, but the memory traces are different in these two branches. But again, there's like very mature programming language techniques, which we proposed in our earlier work. We can actually basically type check your program. And if the compiler passes, you know your program has to be oblivious. And again, this line of work is also very mature. If you are interested, you can check out our open source library. So right now we have released Oblivious map, Oblivious sorting primitives, and there's a lot more we want to do down the road. Okay, so in conclusion, do you need an ORAM? Apparently, if you come to Pittsburgh, you can go to a coffee shop and buy a donut called an ORAM. So do you need an ORAM? Yes, it's delicious. If you come to Pittsburgh, I'll buy you an ORAM. Thank you so much.